I'm Susana Otero. I'm the head of the Advanced Printing Department of AIDO, the Technological Institute of Optics, Color and Imaging. We are in Valencia. And we cooperate with ITENE in the unit Smart Print. We are talking right now about the new printing applications in pharmaceutical packaging. So we are going to review a new area of healthcare. So the new needs we have, the new trends, and the new opportunities this brings to the pharmaceutical packaging. Then we will review the new developments by means of printing technologies and review basic principles of printing technologies, main aspects of print inks, the functional inks, and then the conclusions. I would like to introduce Smart Print, but we are the same people as the last conference, so it's not necessary to do that, but just remember that ITENE and AIDO cooperate together, developing new functionalities in this packaging. So we are talking about smart packaging. ITENE is specialized in packaging solutions and applications, and AIDO is specialized in printing technologies and printing applications. We are working in the field of control and quality of the product, identification and traceability, security and anti-counterfeiting, and innovation through communicative packaging solutions. So, we are in a new era of healthcare towards sustainable, integrated, consumer-centric healthcare solutions. We are talking about that all around healthcare is prevention programs, early diagnosis, targeted treatments, caregiver programs, aftercare, and personal profiling. These give us new needs in healthcare, and these give us new opportunities in pharmaceutical packaging. We are talking about different problems we have to improve, such as patient adherence, cold chain, sensors, E-levels, track and trace security, brand protection, and anti-counterfeiting. We are going to review some of them, and in order to give some ideas about what can we do in our packaging to improve these problems for the healthcare industry. So, regarding to patient adherence, we can understand the extent to which a person's behavior, taking medication, following a diet, and or executing lifestyle change correspond with agreed recommendations from a healthcare provider. But we have a big problem on it. Lack of patients' adherence to prescribed medication poses a tremendous challenges to the global healthcare community. In the USA alone, avoidable medical spending was estimated at $300 billion in 2009. According to the interviewees, on average, adherence levels drop over to the course of the patient journey from 69% of patients filling their first prescription to 43% who continuing their treatment as prescribed after 6 months. Looking specifically at the issue in USA at 2007, survey conducted by the National Community Pharmacists Association revealed that the 49% of respondents admitted to have forgotten a prescribed medicine. 31 of respondents had not filled a prescription they had been given. The 29% of respondents had stopped taking a medicine before the supply ran out. and the 24 of respondents has taken less than the recommended loss. This is a big problem for the healthcare industry. We can see some of the commonly adopted adherence interventions, and we can see that one way is in the packaging and in the printing materials. Brochures, leaflet, cards, and we think the main solution is the interaction between the pharmaceutical packaging with the patient. We have to transfer real-time data. We have to real-time communications with patient and environment, influence behavior of patients, analyze of the compliance and clinical outcome, and real-time compliance data for patients, and real-time clinical outcome from patients. So we have to work in order to improve our packaging, to make this interaction between the packaging and the consumers, the packaging with the patients. Another big problem is the falsified medicines, brand protection and anti-counterfeiting. Falsified medicines are fake medicines that pass themselves off as real, authorized medicines. The phenomenon of falsified medicines is on the increase, with more and more medicines now being falsified. These include expensive medicines, such as anti-cancer medicines, and medicines in high demand, such as antivirals. Falsified medicines are found everywhere in the world. They range from random mixture or of harmful toxic substances to ineffective preparations. Some contain a declared active ingredient and look so similar to genuine products that they deceive health professionals as well as patients. But in every case, the source of a falsified medicine is unknown and its contents unreadable. Falsified medicines are always illegal. They can result in treatment failure or even death. Eliminating them is a considerable public health challenge. Most industrial, we can here see the size of the problem. Most industrialized countries with effective regulatory system and market control of USA or European Union, Australia, and so on, have an extremely low proportion, just 1%. But many countries in Africa and parts of Asia and Latin America have areas where more than 30% of the medicines on sale can be counterfeit. In many of the countries of the former Soviet Union, the proportion of counterfeit medicines is above 20% of the market. But the main problem also is internet. Medicines purchased over the internet from illegal sites that conceal their physical address are counterfeit in over 50% of cases. We have a directive in the European Union to prevent falsified medicines entering the legal supply chain and reaching patients. It introduced harmonized safety and strengthened control measures across Europe by applying new measures, including obligatory features on the outer packaging of medicines to demonstrate that they are authentic. There are other measures, but it's not the interest of this conference, but in this directive is recognized the importance of the pharmaceutical packaging to integrate this kind of solutions. So, as I say before, new developments by means of printing technologies. Why printing technologies? To print these new functionalities in pharmaceutical packaging. Printing is a process for reproducing text and images, typically with ink on a substrate. They can be paper, film, glass, and so on, using printing press. It is often carried out as a large-scale industrial process and is an essential part of publishing and transaction print. The printing process serves to disseminate and reproduce information. Here we can see the main product for the printing industry. And printing is a reproduction process in which printing ink is applied to a printed substrate in order to transmit information, image, graphic text in a repeatable form using an image querying medium. We can find many applications: commercial printing, such as catalogs, brochures, business cards, books, magazines, and newspaper, labels, and packaging. Here in this graph, we can see the main printing technologies. There are different types of printing process. Specifically, how the ink distribution rolls are arranged in the printing press. The major classes of printing process are offset, flexography, review printing, and screen printing. This graph is an overview of printing technologies in which we can make a distinction between technologies requiring a master. This is conventional procedures, and so the other printing technologies are so-called non-impact printing technologies. This one, which do not require a printing plate. The most common non-impact printing technologies are electrophotography and inkjet printing. Each process, therefore, demands an ink that differs in viscosity and drying efficiency, which is possible by fine-tuning the composition. Now we are going to review the main printing technologies in order to review which can we print with these technologies in the pharmaceutical packaging. For example, gravure printing is an intaglio printing technique where the image to be printed is made up of a small depression in the surface of the printing plate. The cells are filled with ink and the excess is scrubbed off the surface with a doctor blade. Then a rubber ink cover roller presses paper onto the surface on the plate and into contact with the ink in the cells. The printing plates are usually made from copper and may be produced by digital engraving. Gravure printing is used for long, high-quality print runs, such as magazines, catalogs, packaging, and printing onto fabric and wallpaper. It is also used for printing postage stamps and decorative plastic laminates. The pros of this technology is high resolution. The dot size is approximately 7 microns and is compatible with functional inks. This kind of inks has low and medium viscosity and is in direct contact of metal gravure cylinder with substrate. The cons are expensive, quite expensive, and static gravure. So the gravure printing is recommended for the height runs applications. Flexography printing is a form of printing process which utilizes a flexible relief plate. It's essentially a modern version of letterpress which can be used for printing on almost any type of substrate. including plastic, metallic films, cellophane, and paper. It is widely used for printing on the non-porous substrates required for various types of food packaging. The pros are soft printing plates and medium resolution. The dot size are about 40 microns. Inks has low and medium viscosity, and the cons are rubber of printing plate can shallow and we don't have an homogeneous thickness. Screen printing is a printing technique that uses woven mesh and ink blocking stencil. The attached stencil forms open areas of mesh that transfer ink or other printable materials which can be pressed through the mesh and sharp edge image onto a substrate. A fill blade is moved across the screen to stencil, forcing up or pumping ink into the mesh opening for transfer by capillarity action during the squeeze stroke. Screen printing is also a stencil method of print making in which a design is imposed on a screen of polyester or other fine mesh. The advantages for this printing technique is the simple process, variable layer of materials. These inks are high viscosity, and the limitations are low resolution. It's a good printing technology for print circuits and some electronic printings, like electroluminescence. Then we have inkjet technology that spray very fine drops of ink on a sheet of paper. These droplets are ionized, which allows them to be directed by magnetic plates in the ink paths. As the paper is fed through the printer, the print head moves back and forth, spraying thousands of these small droplets on the page. Here we can find different types of inkjet technologies. We can find continuous inkjet and drop on demand. The most extended on the market are drop on demand, and we can find thermal and piezoelectric inkjet technologies. The pros are non-impact printing and dynamic imaging. We work with low viscosity inks with a medium resolution, about 20 microns, and waveform variability. The cons are particles in inks and very low layer thickness. Finally, we can find offset printing. Offset is a widely used printing technique where the ink image is transferred from a plate to a rubber blanket, then to the printing surface. When used in combination with the lithography process, which is based on the repulsion of oil and water, the offset technique employs a flat image carrier on which the image to be printed obtains ink from the ink rollers, while the non-printing area tracks a film of water, keeping the non-printing areas ink-free. The pros are high quality of this technique and is mass printing. We use ink with high viscosity and a medium resolution, about 15 microns. The cons are functional printing setup and complex dampening and inking units. It's not quite used for functional printing. There are little inks on market for this technology, for functional printing. Here we can see a comparison between different technologies. we have to fix in layer thickness, because depending on the devices we want to print, could be better one technique or another. For example, for printing electronics, we need very thick layers. So maybe a screen printing is not quite good for this kind of application, or we need inkjet. And another item we have to see is the ink viscosity we need. And it depends on the inks on market. We can do one or another technique, and also the resolution. So here we can see a comparison between the main printing technologies, in which we can see the layer thickness and the viscosity of the ink we need to use. If we need small thickness layer and low viscosity, so we use inkjet or flexo and gravure. But if we need high thickness and high viscosity, we will use screen printing. So it depends on the material, it depends on the device we want to print in our packaging. So regarding to the kind of functionality we choose to print, we will select a type of ink and the most appropriate printing technology. Now we are going to review the basics issues we have to consider regarding to inks. Regarding to structure and components, printing inks are principally made up of colorants, bicols, additives, and carrier substances. Depending on the type of printing process, inks have largely variable flow properties, which range from extremely thin, watery, through high viscous, up to dry. The ink transfer mechanisms and the type fixing on the ink on the substrate principally determine the structure and the components of the printing inks. The ink must dry or cure on the substrate. High differentiation is basically made between physical procedures, such as absorption and evaporation, and chemical drying, such as oxidation and radiation curing. Very often, a combination of dyeing processes is applied. So the inks must have a good adhesion to the substrate surface. And several methods are common. We can see the inks anchored mechanically to the substrate surface, penetrating pores, encasing paper fibers. Here, a certain pressure between ink and carrier substrate is required. Or the inks penetrates into the surface by capillary action. And in the case of extremely smooth surface, the ink is held by means of polar interaction between the ink and substrate. The rheological characteristics of inks is quite important. The setting of consistency of a printing inks has a decisive influence on the productivity and quality of a print job. The consistency can be classified into various individual properties and should be adjusted to match specific printing presses, substrates, printed subjects, spin, and so forth, as optimally as possible. And the most important terms are dynamic viscosity, which can be termed as the inner resistance to flow of the ink. The more viscous an ink, the less easily it's to flow and the more difficult it's to spread into a film. The thixotropy is the characteristic of changes viscous inks from a high viscosity into a significantly lower viscosity. Tag of an ink characterizes the splitting property of an ink film, for instance, between two ink rollers. The greater the tag, the more heat is produced in the rolling unit, and the greater the tendency of fiber particles to pull out from the paper surface. Finally, the shortness is understood to be the flowability of an ink between certain shearing force acts upon it. The physical force between pigments, particles, and the higher molecular vehicle components determine whether an ink is short or long. Very short inks cannot easily be pumped or exhibit bad flow characteristics in the ink fountain. In summarize, ink should have a viscosity appropriate to the printing process. Some inks have butter-like consistency and others have intermediate viscosity. Various polymeric thickening agents are added for this purpose. In this regard, ink chemists are interested in rheology, the study of the relationship between the applied stress and the resulting deformation. The important for the printing is the printability and interaction with the substrate. So, to print new functionalities in the pharmaceutical packaging with the printing technologies, we can classify three main kinds of printing inks. One of these are chromactive materials. We can understand of chromactive materials those which color change as a result of an external phenomenon such as may be electric current, ultraviolet radiation, X-rays, temperature, or pressure. The materials can be classified in thermochromic, photochromic, and electrochromic. Here we can see some examples of photochromic applications or thermochromic for packaging, food packaging, or electrochromic applications. Photochromic are those materials that changing the type of illuminant change color reversibly. Such materials are not in darkness. When sunlight or UV radiations is applied to the molecular structure of the material, it changes color appearance and disappears when the light source ceases. One of the most popular use for photochromic inks is on screen printing garments. As this design illustrates, the inks are transparent until exposed to a UV light source, at which time they take on their specific color characteristics. They return to transparent state when UV exposure is discontinued. For electrochromic applications, electrochromic materials have the property of changing the absorption spectrum, and they usually color to change its oxidation state by applying an external potential difference. We can see a display printing on paper. And thermochromic materials are those materials that change color with temperature. This change may be reversible or irreversible. The color change occurs in a specific temperature change. We could apply this kind of material, for example, to control the cold change for pharmaceutical applications. Another kind of materials are photoactive materials. Photoactive or photoluminescent materials are those which change occurs as a result of different nature of the action of light, or on the other hand are capable of emitting light as a result of some external phenomenon. We can classify as electroluminescence, phosphorescence, and fluorescence. Here we can also see some examples of this kind of materials. For example, a package with electroluminescence lamp. Electroluminescence materials are those that produce bright light of different colors when stimulated electronically, while not emit light. We have also fluorescent, emit light when is excited nanoseconds during its electrons to a higher energy state, generate highlight flash colors. Therefore, the fluorescents require a continuous source of excitation. The last one is phosphorescent. Phosphorescent materials produce visible or invisible lights as a result of incident light of short wavelength. Detectable after the source of excitation has been removed. This is main difference compared to the fluorescence material. Another kind of materials are conductive materials. We can find conductive inks that allow electric current with a minimum resistance. The electric materials not allow electric. Semiconductive materials and barrier materials for encapsulation and to protect the printing devices from oxygen and moisture. With this kind of inks, we can print this kind of applications. Here we can find RFID antenna printing on this, this package, or complex printed circuits for security, track and trace, or patient adherence in pharmaceutical packaging. As my colleague Nuria has told before, we are right now we are researching in two functional printing applications. In the one hand, Smart Cool Pack, development of change temperature indicators to control cold product change, and the other one is a Smart Printed Pack. She has shown before this package in which we have printed some contacts with screen printing and also electroluminescent display to show if the packaging has been open or not. Just finally, we are going to review that there are new needs in healthcare, bring new challenge and new opportunities in pharmaceutical packaging. The market demands new functionalities and added value to the pharmaceutical packaging to solve new problems such as security, brand protection, and anti-counterfeiting, cold chain, patient adherence, track and trace, and so on. The new functionalities in pharmaceutical packaging, on the other hand, must be easy to use for the consumer and low cost. For that reason, printing technologies, offset, flexography, gravure, screen printing, inkjet are the best way to integrate new functionalities in pharmaceutical packaging. It's possible to print new functionalities in the same way, and at the same time, you print text, graphics, and text with CMYK with these new functional inks. There are different smart inks and active materials available to print new functionalities, such as conductive inks, conductors, semiconductors, dielectrics, chromoactive inks, electrochromic, photochromic, thermochromic, photoactive inks, electroluminescence, phosphorescence, and fluorescence, and other inks such as magnetic inks, aromatic inks, and so on. Not all these inks and materials are suitable or available for the whole printing technologies due to the consistency of the printing inks. The best printing technology depends on the device we want to print due to the type of ink, the resolution we need, and the layer thickness you need to obtain. So, as Nuria has said before, maybe we need to mix some printing technologies to print some new developments. And finally, is a big opportunity. Printing smart devices directly to the pharmaceutical packaging in the same printing machine as we print text, graphics, and images solve the main challenge for the pharmaceutical packaging industry. Thank you very much, and sorry for my English.